telling you about the features of vehicle management, just the introduction. Then some outline on the technologies and algorithms. Then a very important thing that is the auto ID procedures, because see, right now in market you have various auto identification procedures. You go to any shopping mall, you will see that there is a barcode and someone is putting some laser on the barcode and they are getting some information. If you go to if you go for any MCQ type of test, now there is some optical mark reader, OMR sheet is given to you where you mark ABCD and then people just put it in some optical mark reader and they get the result. That means the manual labor of checking each of the question is minimized. But then why RFID? When all these technologies are already existing, auto ID procedures are existing, then why are we going for RFID? What are the particular advantages of RFID, radio frequency identification, over these auto ID procedures? That thing we will study. Then the basic architecture of RFID system, its physical principles. That means that will deal with what should be the range of the RFID systems and all those things. Selection criteria for RFID systems, because see, if there is a one-to-one communication, then RFID system should be something else. If there is one-to-many communication, then the RFID system should be something else. So that selection criteria we have to judge, and then accordingly we have to design the RFID system. Then RFID system basically consists of two main things. One is the RFID tag, another is the RFID reader. So we'll learn about RFID tags and RFID readers. And as you know, that since it is a wireless connection, RFID, so the end point of the tag and the end point of the receiver, there will be some antennas. So RFID antennas are also very vital part that you should know how to design RFID antennas so that there is secure transmission and error-free transmission of data, full duplex transmission of data. So here in the introduction, what are the main parts of vehicle management? First thing is that whenever a driver is moving through a crowded place, then he or she should be made aware of the proximity of a pedestrian or another vehicle, so that the clash or accident probability gets reduced. That is one of the very important things. That means whenever there will be some vehicle or some pedestrian or some animal at the proximal range of a vehicle, then the vehicle should be alerted, the driver should be alerted. And another technology which is coming up is that not only alert, but the speed will also drop automatically, because there may be some rash driver who will ignore the alert and he will try to speed up and go. But then some technologies are coming up that after getting the alert, automatically the speed will be decreasing until the alarm goes off. So safety on road is a key concept in any city. Secondly, see, there are speed limit boards which we can find at the vicinity of a hospital, the vicinity of a school. Say in the vicinity of school it is 10 km per hour. That means a vehicle should not speed up more than 10 km per hour. But most of us, we don't listen. Either we don't see or we don't listen. Now over there, if there are some RFID systems, first thing will be there will be some awareness that will be triggered in the car. Second thing, again, as I've told you, that there will be some smart technologies which are coming up. That suppose there is a place where the speed limit is 20 km per hour. Whenever the RFID will detect that thing wirelessly, then automatically the speed will decrease to 20 km per hour. That means even if the driver wants to increase the speed above 20 km per hour, he will not be able to do that. Okay, so that is something which is speed limit control. And then another is electronic toll collection, because see, nowadays still in India we have manual toll collection, as a result of which what happens in many times in busy roads you will see that there is a huge queue of buses and trucks and lorries and cars. So it is time consuming, it is harassing also. And also suppose there is a very emergency, a person wants to go to some emergency duty. Now if he is stuck in some long queue for toll collection, then he will be at a loss. But if toll collection can be made in such a way that the car or a bus can pass with its own speed and the toll will be collected just automatically, then that is very easy to employ also, and that is also very user friendly. There will be no queue, there will be no harassment and all those things. So electronic toll collection is one of the primary features of our RFID tag. Here, I think I should tell you that electronic toll collection is one such application where RFID tags is coming up right now, because it is an open research area, and electronic toll collection is an area where the application is coming up in abroad, not in India. Till now in India it has not come up, so in a very good way. So we'll talk about that also. So as I've told you that in highway, see, one thing is that the way in which electronic toll collection is envisaged is that there will be a reader over in the ceiling that you can see over here. Suppose this is the blue ceiling that you can see. If there is a reader over there, suppose this white car is passing and there is an RFID tag over there. Whenever the white car will pass through this, the reader and the tag will get communicated, and the reader is connected to some base station server, and the tag is a kind of RFID system with some semiconductor chip which has some memory, and in the memory what will we have? We will have the vehicle identification, all the registration numbers and everything, its classification, because see, a car will have different toll, or lorry will have different toll, so the classification will be there, transaction process will be there, and violation handling. Why violation handling? Suppose if there are smart systems, so that whenever this, suppose this white car, it is passing under this blue ceiling and there is a communication, and suppose for this white car the toll is 10 rupees, so 10 rupees will be cut off from its account. Now a cunning driver, what he may do is that he might not keep that balance in his account. Then what will happen? So that is why this violation handling criteria is put in this RFID tag. Then what will happen? That whenever this reader will find no money in his or her account, then the reader's base station will communicate with the traffic base station that this car, and since the car is having all the vehicle identification and classification in its tag, so everything will be communicated to the traffic station that this car has not given any toll, and the traffic station will be taking the suitable actions thereafter. Now, as I've told you about speed limits, so suppose there is one speed limit which is 30 kilometer per hour. Okay, you can see there is a stand over here. Here there is a RFID reader, and what will happen? RFID tag will be say an RFID card tag will be on the bonnet of this car, and this tag will be wirelessly connected to a sensor in the wheel, just above the wheel. So whenever there will be a communication with the reader and the tag will direct the sensor that see the limit should be 30 km per hour, and accordingly that EMU of the car will try to decrease the speed of the car to 30 km per hour, and even if the driver wants to increase the speed above 30 km per hour, he will not be able to do it. Then collision avoidance, as I've told you, that collision avoidance actually uses a proximity detection system. So what happens? Suppose user defined proximity is already there, so it is X meter. So whenever this car, the blue car, this back one, suppose this car has come to a close distance within X meter limit to this front car, then what will happen? So this front car is having one RFID, this back car is also having one RFID. So both of them will be communicating with each other, and this back car will be given a signal that you have come to the close proximity to the front car. Accordingly, the driver should adjust the speed, and as I have told you that smarter technologies are coming up so that automatically the speed will come down. Okay. So see here there are three ranges. This is another smarter technique where the RFID will be programmed in such a way that if it comes to this red region, then there will be collision mitigation. Then over there the speed breaker will automatically come into force. Now if it comes to this pale red region, then there will be collision warning with brakes up. Okay, and whenever it will be in this purple region, then the RFID tag will be saying that there is a collision warning. So that means what is happening? First, the driver is given a collision warning. If he ignores the collision warning, then he will be given another collision warning with brakes up. If he ignores that thing also, then there will be automatic collision mitigation. That means the speed will automatically try decrease. Okay, so that is intelligent vehicular communication. So the vehicle management actually can be segmented into two parts. One is road vehicle communication system and inter-vehicle communication. What is road vehicle communication system? Suppose you are going in a toll tax. In a toll tax, what is the communication? Communication is between the vehicle and the vehicle RFID with the RFID that is situated on the ceiling of the toll tax. That is the road vehicle communication. Suppose in a speed limit case, then what is happening? There is a speed limit board and there is a vehicle. So the communication is between speed limit board and the vehicle. So that is the road vehicle communication. What is inter-vehicle communication? For collision avoidance. Suppose there are two vehicles or three vehicles coming in the close vicinity. Then the alert that you are getting due to the interaction between two vehicular RFIDs, that is known as the inter-vehicle communication. And different methods have been employed, algorithms have been employed. Algorithms are generally fuzzy logic neural network. We'll not discuss these algorithms right now because these are not pertinent to this presentation. That is, I just want to inform you that the various algorithms which are set up, which are used for programming the RFID chipset, are fuzzy logic, neural network. Suppose, for example, in toll tax, the algorithm that we use is generally the geodetic algorithm. So, and different other methods are GPS based method, video imaging method, radar detection method are also there. But these methods, see, GPS based method is already used in your Uber and Ola. Okay, so GPS for giving traffic condition, for giving the information of traffic condition, where the traffic is heavy, where the traffic is light, the shortest route condition like that. But for collision avoidance and all those things, the GPS based method is not that much suitable because GPS cannot is a not high resolution thing. That means if two cars in a very close proximity, GPS cannot identify the two cars separately. So that is a very minute what should I say, drawback of a GPS, that if two things are very in a very close vicinity to each other, GPS will think that thing as a single entity. So GPS based method for traffic management is not a very intelligent thing. And similarly, video imaging is also not an intelligent thing. Why? Because see, we always think that any visual demonstration is the best. But whenever we will be going for video imaging, the memory that will be required for the storage of data or the uploading and the downloading of the data will be huge. So, but a RFID chipset, it comes with a very small data with very small memory, and so video imaging is not a very good way to think about intelligent traffic management, because if we want to employ video imaging, we have to think about the memory part also, which can handle some megabytes of data at a time. That means the throughput, channel capacity, everything will come into account. Radar detection is also having the same drawback as GPS, because we cannot directly use radar detection for identifying two vehicles like that. So RFID tool is an emerging trend of modern technology and vehicle management systems. That now this is one thing, auto ID procedure that I'm talking about while discussing the outline. See, what is auto ID procedure? It is a broad term given to a host of technologies that are used to help machines for identifying objects. One of the very prevalent example is that if you go to any shopping mall, you will buy something and there is a barcode. The barcode will be scanned by some laser, and then all the details of that item will be gone in the computer screen. So what is happening? The barcode is the tag, the laser is the reader, and the reader is connected to the to a computer. Okay, so whenever the reader is reading the tag, it is retrieving the information from the tag and it is feeding it to the computer, and accordingly the computer is running the program. Okay, so that is one thing. Another one is your OMR sheets, that example that I have given you. Okay, so another example is smart cards, because in metro stations and everywhere you are having smart cards. So smart card is also having your relevant information. When you are swiping the smart card, according to the information, the thing is going on. And even in your the ATM card also, it is also a smart card. Okay. So when these kinds of auto ID procedures are already in existence, why are we going for RFID procedure? That is the main question. What are the particular advantages of RFID procedure over the other existing auto ID procedures? Okay, one thing I can say that smart cards are not that much intelligent, because smart card is still having some manual involvement, some touching and all those things. But what about this OMR, or what about this barcode reading method? What is the advantage of RFID over barcode reading method? Okay, why the industries are so much interested in RFID? So here is just one thing that is given over here. This auto ID means auto ID is having this optical character recognition, which is there in OMR sheet. Barcode system. Biometric is also another kind of auto ID system where it will scan your eye retina or it will scan your fingerprint. Even right now, nowadays, the technologies have come up so that you don't have to put your finger on a particular switch. You can put it at a particular distance, and then your fingerprint can be read like that. So no touching is involved like over there. So biometric system is also a kind of auto ID procedure. And then there is this smart card procedures are there, and then RFID systems are there. What I am suggesting is that this RFID procedure is advantageous over all those auto ID procedures. Why? There is a comparison sheet which is given over here. The first thing is memory, because see, by now we have understood that video visualization of anything is not feasible for vehicle management or as such for any other thing, because video will require very high memory capacity, and whenever we will try to design any such device with very high memory capacity, then the expense will become excessively high. So we need smaller memory. The thing is that a barcode and the RFID tag will take the same amount of space. But see, a barcode will having a data quantity of 1 to 100 bytes. OMR will be having that same thing also. But the RFID, you see, it is having it can store data quantity from 16 to 64 kilobytes, and that is enough for storing data in word form. Second is data density. What is actually meant by data density? Data density means if one RFID tag or if one RFID, rather if one device is able to communicate with 5 devices at a time, that is the handling capacity of a device, and that is that signifies what is the data density of one particular device. So now see, if there is a barcode system, that laser can read only one barcode at a time, not 5 barcodes at a time. OMR sheet also the same thing. The biometric system, yes, it can study the retina of 2 people at a time. But for RFID systems, the data density is very high, very high, because for a large, there are RFID readers where one RFID reader can communicate to 5 RFID tags. For example, I'll tell you one thing. Suppose there is a speed limit board of 30 km per hour, and there are 5 cars which are coming over there. Now, if the reader is able to communicate with only one car, then for one car the speed limit will go down to 30 km per hour. But what will happen to the other cars? There, for the other cars, it will be higher than 30 km per hour. So the RFID systems have very high data density, such that RFID reader which is employed in the speed limit board, that will be able to communicate with say 10 cars at a time. So the 10 cars which are passing at a time with in a chunk, for all the 10 cars the speed limit will come down to 30 km per hour. So that is why RFID is a better preferred technique over there, because its data density or data handling capacity is very high. Third is machine readability. Yes, machine readability for barcode, OMR, and everything is good, but for biometry, you know that to set up a biometry system, the machine readability, it is an expensive thing. And we have seen that RFID is also having some very good machine readability. Machine readability means the ability of the reader to retrieve the tag very easily. That is known as machine readability. And then the readability by people. Here comes the security part. It means for RFID, the readability by people is almost impossible, because whenever there is a communication from the reader to the tag, there is an encrypted data communication. Because so the data which is encrypted from the reader can only be read by the tag. So even if there is a third party who wants to intercept the data, here I am not talking about exactly about vehicle management. I am talking about in general RFID tag. So For a reader, there is a block known as encryption block that I will show you later, where the data is encrypted and then it is radiated by the antenna. So if a third party wants to intercept that data, that is practically impossible for an RFID. Now, influence of direction and position. If you take a smart card, suppose an ATM card, you cannot swipe it in your preferred direction. It has to be swiped at a particular direction to get the information, to feed the information to the server. And for barcode and OMR also, I mean, yes, you can read the barcode at some distance, but you will notice one thing: if the barcode is orthogonal to the laser light, then you can never read the information which is there in the barcode. So there is some limitation of using barcode also, because the influence of direction and position is there in the barcode also. But for RFID systems, there is no influence of direction and position. A tag, the orientation of a tag with respect to a reader can be at any direction, but the reader can still read the tag at any direction. Why? That thing I will discuss later. Then the operating costs are none. Once you set up the RFID system, there is no other operating cost. Yeah, one more important thing is reading speed. So reading speed of barcode, OMR, biometry, smart card are low, but the reading speed of RFID is very high, because RFID works in megahertz or gigahertz range. Since it works in megahertz or gigahertz in a very high frequency range, that is why its reading speed is very high. And another very important unique character of RFID is that its distance, the distance of the reader and the tag. In general, if you want to read a barcode with a laser light, you will not be able to read a barcode with a laser light after 50 centimeters of distance. Or suppose the barcode is one room, the laser light is in another room, the laser light cannot penetrate to the barcode, so it cannot be read. The same thing is for OMR also. The same thing is for biometry. And still now biometry, although wireless biometry has come, non-touch biometry has come, but for biometry, the finger or the eye has to be kept in a very close proximity to the system. And smart card, it requires direct contact, but for RFID, the RFID reader can read the RFID tag even from a distance of 5 meters or 10 meters. And another very important thing is that since it is radio frequency, and as you know that radio frequency can penetrate through walls or any barriers, so even if there is some barrier, a physical barrier between a car and the RFID reader, then also the RFID reader can read the RFID tag which is implanted on the car. Okay, so that is one more advantage of RFID system, which is not available for other auto ID procedures. This is the basic design of an RFID. And always keep one thing in mind: RFID works in digital domain. That means the data which is stored and the data which is stored is always in the digital domain. The data which is stored, that is first modulated, and then that modulated frequency is up converted to a gigahertz frequency, and then the RFID antenna radiates that frequency. But the data which is there in the RFID chipset is always in digital form. Keep this thing in mind. It is not in analog form. Okay. Now this is the basic architecture of an RFID system. So what happens? This is a tag with transponders, and this is the antenna of the reader. So whenever the reader and the tag are in the readable zone, then what happens? The reader antenna radiates some energy to the tag, and whenever the tag will sense the energy, the tag chipset will be on. And whenever the tag chipset will be on, the data which is there in the chipset, that data will be sent by the tag antenna towards the reader antenna. And one thing may also happen, that data may also be sent from the reader antenna to the chipset antenna. For example, in a speed limit, what will be the reader antenna doing? The reader antenna will be directing the tag antenna that your speed limit should come down to 20 km/h. That means in that particular system, the reader antenna is sending some data to the tag antenna. along with the energy to make the tag antenna on, the tag chipset on rather. Okay. Now for a toll tag system, what will happen? Whenever the reader and the tag will be in close proximity, the reader will just send the energy, the microwave frequency, which will make the chipset on, and the vehicle identification number, the bank details, the transaction details, everything will be sent from the tag to the reader. That means for that particular scenario of toll collection, the data will be from tag to the antenna to the reader. But for say speed limit, the data will be from reader to the antenna to the tag. So that is why the data is bidirectional over here, but the energy will be unidirectional from the reader to the tag. Why? Because see, if the tag is always kept on, then there will be unnecessary energy consumption. So the tag should be made on whenever it will be sensing a reader. So that is why reader sends out the energy, and whenever that energy is sensed by the tag chipset gets on. Okay, and then either the tag sends some energy, some data, or reader sends some data, and that data is processed by the reader module, RFID reader module, because this reader module will have to again demodulate the data, get it in the digital form, and then it has to be fed to the host computer for further processing. So this is the basic backbone of your RFID system. Now the physical principles. If you go to the this slide, see, this is the reader module, this is the tag module. So there is a particular distance. Now since the reader and the tag both are there, in both the cases there are two antennas over here. So there are two terms that is known as far field and near field. So any antenna, why the far field and near field parts are important? Because if the distance is within the near field, then the reading will be somewhat different. If it is within the far field, the reading will be somewhat different. Now first you have to know what is the near field and what is the far field. See, if you take suppose if you take any RLC circuit, say if you say any RLC circuit, then the heat dissipation is due to what thing? Can you tell me? The heat dissipation in the RLC circuit is due to what thing? Due to what phenomenon? Suppose there is a RLC circuit, then suppose the circuit is working for 1 hour, then the circuit will be heated up. Why the circuit heats up? Any idea? Okay. Okay, let me tell you the answer. Every circuit has a resistive part, and the circuit heats up due to the ohmic loss of the resistive part, I square RT. Okay, so the heating up of the circuit is the energy that is obtainable by the user. That is the ohmic loss. And in the RLC circuit, in the L part, there will be some magnetic energy storage, and the capacitive part, there will be some electric energy storage, which as such we cannot retrieve. Okay, so an energy, any power in a circuit is having basically two parts. One is the obtainable power, and another is the non-obtainable power. So generally, the obtainable power we term it as the active power, and the non-obtainable power we term it as the reactive power. So the same thing is for tag antennas or reader antennas. An antenna is what? It is basically radiating some power in the wireless domain. So whenever it will be radiating some power in the wireless domain, then the power will be having two parts. One is the active part, another is the reactive part. Now, from the antenna, if we move away, there will be a margin. Suppose x meter margin. So from the antenna up to this x meter, the reactive part of the power will be dominant. That means the power will be either electrostatic or magnetostatic stored energy. It will be oscillating power. So that zone is known as the near field. and after we cross the near field margin, the power will be predominantly resistive, active power. So in that is known as the far field. So a tag antenna may be within the near field region of the reader antenna, maybe in the far field region of the reader antenna. So if the tag antenna is within the near field region of a reader antenna, then how the tag will interact with the reader, that is one principle. And if it is in the far field region of the reader antenna, then how it will interact. So in the near field, what happens is that there is Faraday's principle of magnetic induction that will be clear from this figure. See here, the RFID reader, the radiated energy that I have shown you, it is in the near field. Okay, and this RFID tag is within the near field. So whenever RFID tag is having its own radiated power, energy. So whenever this RFID tag will be within this near field, then the flux that will be crossed by this due to the flux of these lines which will be crossed by the RFID tag, this will be varying with time, and whenever this flux will be changing with time, there will be some electromagnetic induction, and that induced voltage will be used to read the RFID tag data over here. Okay, so whenever the RFID tag will be in the near field region of the reader, then the reading of the tag by the reader will be due to the electromagnetic induction according to Faraday's law. And whenever it will be in the far field region, then what will happen? So here see now, RFID tag is in the far field region of the RFID reader. Then what will happen? That the reader will capture, the tag will capture the far field energy of the reader, and then it will backscatter the same thing. So in the previous thing, it is not backscattering. In the previous thing, the voltage is induced due to change of flux. But in the far field, what is happening? The radiation from the reader is reflected by the tag, and that reflected wave is again read by the reader to retrieve the data from the RFID tag. So in the far field, it is a backscattering phenomenon, and in the near field, it is a Faraday's law of induction phenomenon. Now the selection criteria of RFID systems, first one is the obviously the operating frequency, because if you want to operate it in the microwave range, it operates generally from 2.45 to 5.8 gigahertz. It operates in the UHF or HF range, which is from 100 kilohertz to 30 megahertz. So if you want to operate an RFID reader and RFID tag in the near field region, then we will always choose the UHF range or HF range, that is high frequency range, which is from 100 kilohertz to 30 megahertz. But if we want to make the RFID reader and the tag interact with each other in the far field region, then the frequency range should be in the gigahertz range, which is from 2.45 to 5.8 gigahertz. So, and another thing is that the other things that are required are positional accuracy of the transponder, the minimum distance, and the speed of the transponder in the integration zone. That means, suppose if you want RFID to be used in toll tax. So in a toll tax, suppose the car is going at 60 km per hour. So the reader and the tag should be interacting very fast. So in that case, we should be preferring the gigahertz range instead of the low frequency, instead of the megahertz range. Okay, so in that way, we have to keep in mind that what should be the speed of the interaction. So that is one very important thing. Second thing is the positional accuracy of the transponder. For example, suppose you want a speed limit case. If you see the speed limit case, that means what is happening? That one reader will be able to interact with 5 or 7 cars, tags. So that means the reader should be able to have an omnidirectional pattern, so that it is able to intercept the cars which are coming from any direction. Okay, so this positional accuracy is also having to be kept in mind. Accordingly, your reader and tag should be designed. Memory capacity I have already discussed. And security requirements. See, suppose if you want to use a RFID tag in a closed environment, then obviously you have to use a encrypted data. But suppose for public use, if you want to use a RFID tag, for suppose for speed limit or for collision avoidance, then you cannot directly give a very high-end encryption encrypted data, because my encrypted data will be different from another person X's encrypted data. So when my car will be in close proximity with X's car, then what will happen? Both of them are having encrypted data. None will be able to read each other, and so the RFID tag for proximity detection will be meaningless. So in those cases, the encryption is not required. But for closed environments, suppose for very closed industrial applications, then we need some encryption data. That means that provision is also there in RFID tag where we can include encrypted data. Now RFID frequency table, bands table. Here you can see that as you are moving to from kilohertz to gigahertz range, your reading range is increasing. That is why I have told you that you have to determine what is the reading range. If the reading range is very high, then you should be using the gigahertz range. Okay, and also you see whenever you are moving from kilohertz to gigahertz range, the data speed is also going high. So that is why where interaction time is very low, over there you have to go to gigahertz range. And power source, acha, tags are generally passive tags. That means the tag will be on whenever it will be sensing a reader. Okay, but there are some hybrid tags also, and there are some active tags also. Generally, suppose when a tag is operating in the gigahertz range, it is a hybrid tag. It is having a active module. It is also having a passive module. But whenever you are going to very high frequency, that means from say 3.1 gigahertz to 10 gigahertz, then the tags are active tags, because more the frequency, more the attenuation of the wave. Keep this thing in mind. So whenever the frequency is say 10 gigahertz, then the attenuation of the signal will be very high. So even for covering a very small distance, suppose the reader antenna is emanating a power of 1 volt. By the time it will come to the tag antenna, it will be reduced to say 1 millivolt, which will be insufficient to make the chipset on. So in that case, you have to use active and active tags only, where the semiconductor device will be always on. Okay, so keeping in mind these things, you have to design your RFID system. And as you can see from the table, for vehicle management, we generally use this 2.45 gigahertz to 5.8 gigahertz range. And generally for this, for vehicle management, we use passive tags. But there is a hybrid model, because every car comes with a battery. So the source of power can be taken from the battery. Okay. Now coming to the RFID tag design actually. So generally is a planar design. First we take a substrate. Okay, the substrate may be paper, the substrate may be any PVC board. So substrate should be a good dielectric. Okay, that means a dielectric whose dielectric constant or relative permittivity should be at least more than 3.5. Okay, so on that substrate we print an antenna. Antenna can be a conductive link, or some copper deposition can be given on the antenna on the substrate. So after the design of the antenna, it has to be impregnated with the chipset, because the semiconductor chipset will be responsible for data storage and for interaction with the tag. And antenna is nothing but it is a passive device. It will just sense the reader. It will just sense the reader signal. After sensing the reader signal, the necessary signal processing and the necessary retrieval of data should be done by the semiconductor chipset. So the antenna and should be impregnated with the semiconductor chipset. And here then comes one very important term, that is impedance matching. Because suppose the chipset impedance is a complex, say 5 plus J2 ohm, and the antenna impedance is say 10 ohm. Okay, so there will be a huge mismatch. So what happens if there is a huge mismatch between the antenna and the chipset? What does it say from your maximum power transfer theory? What does it say? It says that the load impedance should be conjugate of the Thevenin resistance of the Thevenin impedance of the rest of the circuit. Okay, then what happens? Then the maximum power gets transferred. Otherwise, what happens? In the same is for the chipset design here also. The antenna impedance and the chipset impedance, because the chipset is the low, the chipset impedance should be a conjugate pair. Otherwise, what will happen? Whatever power that the antenna is receiving, it will not be able to transfer the full power to the chipset. Suppose it is receiving 5-volt power. Whenever the 5-volt power will come to the chipset will reflect some amount of power. So it will be reflecting say 2 volt amount of power. Then what will happen? The incident wave and the reflected wave will be superimposing, and there will be some standing wave formation. And if there is a standing wave formation, then what happens? There is no progression of power. The power gets stagnant within a confined space. So there will be some loss of power. So that is why the chipset and the antenna impedance should be matched. That is a very important thing. And then after doing that thing, there should be some overlay. That means there should be some covering. That will also be done by using some dielectric parts. So that is the basic design, physical design of a RFID tag. So as again I have told you that there are generally 3 kinds of tags. One is passive tag, another is active tag, another is hybrid or semi-passive tag. So active tags will be required, will be essentially required if I use it in very very high frequencies domain. Suppose more than 3 gigahertz domain. Suppose 10 gigahertz domain, as I have told you, because there will be some problem of signal attenuation as the signal will come from the reader to the tag. So when the signal will be coming from reader to the tag, that signal will be having that much power which can be used only for signal processing. That power will not be enough to make the chipset on. So for that thing, you have to give an independent power source to the semiconductor chip to make it on in RFID tag. Okay, so that is fully active tag. Semi-passive tag means what? That is a hybrid kind that will be having an active model and also a passive model. And passive tags are what? Those who are only having, those who are dependent only on the energy of the reader. And that thing, those tags are used only in megahertz range, and also when the reader and the tag are in very close proximity to each other, so that there is no such attenuation of the signal from while coming from the reader to the tag. Now, RFID tag memory, there are again 3 kinds of memory. One is read-only memory. For example, if you think about the toll tags, then what is happening? The RFID tag is storing the data of the vehicle identification number, the data of the banking details, the data of the violation handling for information. The reader is only reading that information from the tag, and accordingly, the billing is done by the computer which is connected to the reader. And also, if the billing fails, then the thing is also conveyed by the computer which is connected to the reader to the nearest traffic station. So in that case, the tag will be acting only as read-only tag. That means the reader will only retrieve the information from the tag and it will process that information. That's it. Write once, read many means what? So there is a flash memory. Whenever that flash memory will be on, then the data will be cleared off, and you can use the new set of data on the tag, and the tag will be functioning accordingly. Now, until and unless that flash memory is on again, the tag will be acting as a read-only tag only. But there is a provision. What is the difference between the first one and the second one? That there is a provision to flash off the memory of that tag and again rewriting it or reprogramming it. Okay, and read-write tag means what? It is a full duplex kind of communication where a reader, if it feels while in the interaction, if it feels that there is some requirement of writing some data on the tag, then it can be able to do that instantly. So that is read-write data. That means a reader can write the data on the tag as and when required. So this is the comparison that is given over here. So read-write tags are having very high range as compared to passive tags, and onboard power supply I've already discussed that passive tags don't have any onboard power supply. Semi-passive and active tags have it. Communication pattern is passive for passive, and semi-passive is passive, and for active tags it's proactive. That means in active tags the tag can also initiate communication with the reader. Okay, so and the other things are very general terms. These are some pictures of RFID tags which were previously used. So this is a kind of paper tag, where a tag is designed on a paper substrate. Okay, this is a glue tag, that where the tag can be designed on a glue substrate. That is one of the very important aspect of RFID tags, is that a tag can be designed on any dielectric substrate, provided its permittivity is quite high. Okay, now comes the RFID reader. So here the transponder is defining the tag. Okay, so first what happens, the reader is always connected to a master computer, either in a wired fashion or in a wireless fashion. Okay, so the master computer is already having a program which is instantly running on it. So that program is sending some command to the reader. According to that command, the reader will be giving out signal to the tag. Okay, and as per that signal, the tag will be giving some response. For example, in a toll tax, what is the master computer commanding to the reader? That you have to read the vehicle identification number, the bank details, and all those things from the tag. So getting that instruction from the master computer, the reader will be sending out that same instruction to the transponder, that you give those information to me. Accordingly, the transponder, whenever it will be receiving that its chipset will be processing that signal, and from the chipset storage memory, it will give out that information. That is the response. The information will be given to the reader. The reader will read it, and then it will pass that information to the master computer for further processing. So this is the workflow of the reader and the tag. Okay, so according to the workflow, the reader will be designed. So this is a very generalized reader block diagram. Here what happens, the application computer commands something to the reader. Okay, this is a reader block. Now here you can give some encryption block, you may not give some encryption block, that is up to you. So if there is some encryption block, then the data will be encrypted first. Data will be encrypted and it will be sent to the high frequency interface. What will high frequency interface do? See, whenever the data is there in the digital domain, it is working the clock frequency. That means very low frequency. Now that thing will be modulated. Now digital modulation will be in general either QPSK or FSK. So digital modulation takes place in say kilohertz range. Okay. After modulation is taking place in the kilohertz range, you cannot send out the kilohertz range frequency by the reader antenna for vehicle management, because you know for vehicle management the range is from 2.45 to 5.8 gigahertz. Okay. So from kilohertz range you have to up convert the frequency to the gigahertz range through this high frequency interface. Okay, and from that high frequency interface, the data will go to the antenna, and then the antenna will radiate the same data. Okay, here one thing is that reader may have more than one antennas, and second thing, the reader should have the ability to read multiple tags at a time, because suppose for collision avoidance or for speed limit check, a reader should have to interact with many vehicles. So the reader should be designed in such a way that it should be reading more than one tag at a time. Okay, and also the channel should be full duplex. That means the reader channel should allow two-way transmission of data. So these are some RFID readers. These are fixed reader which are generally employed in toll tax. These are handheld readers, and these are some mobile readers which are very portable readers. This is a control section of the RFID. So what does it do? The data is input to a RS-232 port, and from there it goes to the microprocessor. The microprocessor has a programming which sends the data to the cryptography part. Accordingly, the signal will be encrypted, and then it is sent to the RAM-ROM part. Okay. So the data will be sent to the RAM-ROM part. Accordingly, the data will be processed and it will come into the cryptographic part, and from there again it will go to the high frequency interface, and from there to the antenna. Okay. So the algorithm which is there, suppose an anti-collision algorithm or any algorithm or speed check algorithm, that particular algorithm is fed to the microprocessor. Accordingly, that data will be executed. Okay, this is discussed. Now, there are three kinds of data transfer for RFID systems. First is half duplex. That means alternate data connection transfer between the reader and the tag. That means when the tag will be transferring data, reader will not be able to transfer the data, and vice versa. Full duplex means the reader and the tag can be communicating with each other at a time. The reader can be able to send the data, and also the tag can also be able to send the data at a time. And sequential system means the system will be half duplex, and also the energy will be given out in spurts. The energy will not be given out continuously from the reader. If you look into this signal, this figure, then it will be clear to you. For full duplex, the energy is continuously given out by the reader. Okay, and see, downlink is going. Suppose if it is a digital domain. In the digital domain, the communication takes place in packets of data. Okay, so suppose downlink packets of data are going like this. See, downlink packets of data and uplink packets of data. Downlink means from reader to tag. Uplink means from tag to reader. Okay, so see, the downlink data packets and the uplink data packets are overlapping with each other. That means I can say that it is full duplex communication. That means for this part, you see, the data is going from tag to and from reader to tag, and also coming from tag to reader at a time. So it is full duplex. In half duplex, the energy is continuously being emanated by the reader antenna. But see, the packet, when the downlink packet is sent, uplink packet is not sent. After downlink packet is ending, uplink packet is sent. Okay, so that is the half duplex. Now for sequential transfer, you see, only during downlink sending of packet, energy is sent, but while sending the uplink packet, it is not sent. That means sequential data sending is only available in active tags, because it is not it will not be able to it is not available in passive tags, because see, during uplink, that means from while sending data from the tag to the antenna to the reader, there is no energy transfer from reader. That means during the uplink part of the data transfer, the energy is the tag is solely dependent upon its own source of energy. Okay, so that is only possible for active tags. So sequential data transfer is only possible for active tags, where only during the downlink part energy will be given out by the reader. Okay. Now the basic operating principle of RFID readers are either inductive magnetic electromagnetic. There are three steps which you should keep in mind. One is the inductive coupled system, the communication sequence that we want, and the data transmission procedure that we want. So first is the inductively coupled system, which is available for both full duplex and half duplex mode of communication. And inductively coupled, as you know, as the term says, that inductively coupled means that it will be using the Faraday's law of electromagnetics, and whenever it will be using the Faraday's law of induction, that means the tag and the reader will be in the near field region. Okay, so whenever they will be in the near field region, as we have discussed in our previous table, the frequency of operation will be very low. That means it will be from the in the kilohertz to 135 kilohertz to 13.56 megahertz range. Now, how the thing operates? If you look into the block diagram during transmission, a quartz oscillator gives the oscillation frequency. Okay, now data is a binary coded data. Okay, so it is a binary line coded data. So this binary line coded data will be modulated by this oscillation frequency, and the modulation that is generally preferred over here is ASK or binary PSK. If we don't go for QPSK, or for FSK, because there is a particular reason for that. See, here the tag and the reader are in close proximity to each other in the near field vision. That means the distance between each other is very less. So if the distance between each other is very less, then the wireless channel
Sir, it's not audible, sir.
Sir, it's not audible.
So can you please tell me that up to which part have you listened? Try to again start, because I couldn't see that you are not audible. So after say after 7 or 8 minutes, I can see that you are not audible. So if you can just tell me that up to which slide you have heard, then after that I can start again.
Inductive coupled system, sir.
Coupled system,
Inductive
inductively
coupled.
coupled system. Yeah,
Yes,
okay.
sir.
Inductively coupled system you have heard, right?
Yes, sir.
Okay, okay. After that I will start. So is the screen visible to you, all of you?
Yes, yes, sir.
Okay, okay, okay. If the screen is not visible, then just tell me. Okay. So I think up to this you have heard inductively coupled system, right? Okay. So from here I think you have heard microwave systems up to. Okay, okay. So see what happens in half duplex microwave systems. So here, as I've told you, that in vehicle management, generally the frequency of operation is from 2.45 to 3.8 gigahertz. So here there is one particular block, that is this directional coupler block, which is employed. Why, I will tell you that see, a quartz oscillator is not able to oscillate at 2.45 gigahertz. You will not get any such kind of quartz oscillator in market. So suppose you are using a 76 megahertz quartz oscillator, and then now when the data will be modulated with this frequency, here we in general use QPSK modulator, because as I've told you that for microwave RFID tags, they work in your far field region. So as the distance increases between the tag and the reader in far field region,
Hello.
yes, yes, am I audible? Am I audible? Okay, okay. Okay, so you can see the screen, right? Can you see the screen? Okay, okay. So here the modulation is which is employed is QPSK modulation. Why I tell you that whenever you are using now, since it is in your gigahertz range, so the antennas will be working in the far field region. Now, whenever they will be working in the far field region, the distance between the tag and the reader will be high. Now, whenever the distance between the tag and the reader will be high, then there will be the error probability will also increase. So, if the error probability increases, of error probability of the data bits increases, then we have to employ a kind of modulation, digital modulation system which is most immune to noise, and in that case QPSK is the digital modulation system which is most immune to noise. So I'll be using the QPSK modulation system over here. Now the modulated signal is of 76 megahertz frequency, but I need 2.45 gigahertz. So what I will do, I'll be using a frequency multiplier. Okay, so I'll be using a frequency multiplier to up convert it to 2.45 gigahertz. I'll amplify it and I'll be feeding it to a directional coupler. Now a directional coupler has two output ports. Okay, so one port will be used for sending the signal from the reader to the tag, and one port will be used to receiving the signal from the tag to the reader. Why the ports are separated? Because in microwave frequency, if we use the same port for the same frequency of signal incoming and outgoing, then there will be a huge standing wave formation over here, as a result of which the microwave energy will not propagate. So that is why we have separated the input and the output. Okay, so the signal will be given out from one port to the tag, and while the signal is coming to the from the tag to the antenna, it will be received in this port, and then it will be passed to the amplifier. Now, before amplifier, there will be a band pass filter to eliminate the out of band noise, and then there will be amplifier. What will be the microwave receiver doing? The microwave receiver will down convert the signal to again 76 megahertz, and then it will demodulate the QPSK modulation, and the received data will be given to the computer. Okay. So the third one is sequential system. Now, as I've told you that, acha, am I audible? Am I audible?
Yes, sir.
Okay, okay. So sequential system, as I've told you, that here only during the downlink part the energy will be sent from the reader, but for the uplink part energy will not be sent from the reader. So basically the block diagram is same. There will be an oscillator, there will be a modulator, there will be an amplifier and up converter over here. And in the receiver section, there will be a band pass filter and amplifier and then demodulator over here. But here there is a switching section. While the data will be transmitted from the reader to the tag, this switch will be on, and while it will be coming from the tag to the reader, then the switch will come to this part. Okay. So there will be instantaneous switching between the transmitter and the receiver mode. Okay. So now I will be talking about some RFID antenna design. I have told you before also, but now again, see, the RFID reader antenna should be a circular polarized. Why? Because suppose the RFID reader is in some one direction, RFID reader antenna, and the RFID tag antenna say it is at 30-degree angle, it is making a 30-degree angle with respect to the RFID reader. So when the electric field from the RFID tag will come to the RFID reader, the power that will be received will be mod of E square cos square theta. Okay, now cos square theta will be always less than 1. So mod of E square cos square theta will always be less than mod of E square. So that means if the tag antenna is not exactly parallel to the rear antenna, so then there will be some loss of power which will be coming from the tag to the reader antenna due to the polarization mismatch. But if the reader antenna is a circular polarized antenna, that means circular polarized antenna means what? The electric field of the antenna is constantly rotating in a circular fashion. So if the electric field is constantly rotating in the circular fashion, then from whatever angle the receiving electric field will come, that exact power will be extracted from that receiving field by the reader antenna. So that is why the RFID reader antenna should always be a circular polarized antenna. Second thing, the RFID tag antenna should be an omnidirectional antenna. That means the tag antenna should be able to communicate to the reader antenna from any direction. Why? Suppose in a speed limit case, okay, suppose there is a 3-lane road with a speed limit board. Now the car is in the third lane in one scenario. In the next scenario, say the car is in the first lane. Now, if the car will not be able, the tag antenna of the car will not be able to cover the entire region around it in the horizontal plane, then what will happen? When the car will be in the third plane, it will be able to read the sense the reader antenna. But if it goes to the first plane, it will miss out the reader antenna. So that is why the tag antenna should always be omnidirectional in nature. That is the second part. And what is the third part? The third part is the tag antenna impedance should be conjugately matched with the chipset of the tag. As I have told you, because of maximum power transfer from the tag to the chipset. Okay, so these are the three parts that you have to keep in mind while designing the RFID antenna. Now the other design criteria is one is the read range. So R is the read range, that is equal to lambda by 4 pi root over EIRT GT tau by PG. Okay, so EIRP is effective isotropic radiated power, which is given by power of the transmitted antenna into gain of the transmitted antenna. So why this equation is very important? Because according to the read range R, the power of the transmitted antenna will be determined, PT. So EIRP is equal to PT into GT. So if R is more, if the read range is more, then the power of the transmitted antenna should be more. And if the read range is less, then obviously the power of the transmitted antenna should be less. Okay. Second and very important thing is the operating frequency, because you know, if we move higher in frequency, then the size of the antenna or the size of the chipset will also decrease. So as per the operating frequency, the layout size will also be increasing or decreasing. So that is one very important thing to determine what should be the operating frequency, so that the size of the layout area can be determined. Now, these are some kinds of typical tag antenna designs. So, these are the particular kinds of tag antennas which will be employed in your vehicle management. These are known as dipole tag antennas. Okay. And the gap that you are seeing, in this gap, the chipset is included. Over here also, if you see a gap, this gap, that chipset is included. Now see, the difference from this to this structure is that here, above that gap, there is another meander line. Now this meander line is an extra structure which is used to conjugately match the antenna impedance with the chipset impedance. For example, suppose the chipset impedance is 10 plus J2. Okay, so what should be the antenna impedance then? If the chipset impedance is 10 plus J2, what should be the antenna impedance for maximum power transfer? Can anyone of you tell me? If the chipset impedance is 10 plus J2, what should be the antenna impedance for maximum power transfer? Conjugate, yes, but what should be the value of the conjugate? Conjugate is the correct answer, but what should be the value of the conjugate? Okay, so the value of the conjugate will be 10 minus J2. Okay, so minus J2 means what? It is capacitive or inductive? Minus J2 means what? It is capacitive or inductive? Yes, capacitive. So that means to conjugate match this chipset with the antenna, I have to introduce a capacitive element so that it can compensate the inductive element of the chipset. So the capacitive element and the inductive element will be cancelling it out, and I will be getting only the resistive element, which is the fundamental of AC resonance circuit. Okay, so that is why these kinds of meanders are sometimes placed above the chipset to conjugate match the chipset impedance. Now these are some practical tag antenna designs. This is some fan shaped Mendel line. These are also known as log periodic antennas also. Now sometimes what happens that I want the tag. Sometimes what happens is that I want the tag to be designed for a dual frequency operation. Suppose at 2.45 gigahertz and at 3.5 gigahertz. So the tag should be able to, for example, suppose the one tag will be able to communicate with the reader of the toll and also with the reader of the speed limit. So the reader of the toll, say it is operating at 5 gigahertz because it will be communicate with very fast moving vehicles, and say the reader of the toll is operating at 3 gigahertz. So the tag will be able to should be able to operate at both 5 gigahertz and 3 gigahertz. Now you can say that I can use 2 or 3 different kinds of tag, but that is not an intelligent design procedure, because for that thing you will need more layout area, more copper, more tag design technology. But if I can use only a single tag design which will be able to operate in both the frequencies, then it will be very much advantageous for me. So here this design is a dual band tag design. You see, this fan shaped antenna is one antenna, and below the fan shaped antenna, see, there is an L shaped parasitic element. So what happens? The energy from this fan shaped element is coupled to this L shaped element. So suppose this fan shaped element is operating at 2.4 gigahertz. Now the energy from this will be coupled to this L shaped element, which is at the back side of this antenna, and this L shaped element is designed in such a way that it will be resonating at the 5.4 gigahertz. Okay, so this element is getting energy from the coupling phenomenon from this fan shaped element. Okay, so that is why this antenna will be operating at two bands. So these are some kinds of operations, dual band operations, the dual band tag antennas that are also designed. Tag antennas are also designed on optically transparent flexible polymers also. Why? Because if we use flexible polymers, if we can design a tag antenna on flexible polymer, I can put that tag antenna at any part of my vehicle. That means it is having a very flexible design. If I use a very hard substrate, suppose for example, if I use a very hard wooden substrate, so the wooden substrate will be having a particular kind of shape. I cannot bend that shape according to the shape of the roof of the car or according to the shape of the bonnet of the car. But if I use a flexible substrate, and if I can print an antenna on the flexible substrate, I can antenna along with the chipset with the flexible substrate. So the flexible substrate can be bent according to the configuration of the antenna roof of the car roof of the car bonnet. Okay, so research is also going on for developing DAC systems as a whole, antenna along with chip, on flexible dielectric substrates, which can be bent according to the structure of the car. Okay. So these are some kinds of radar antennas. I told you what's the radar antenna criterion. This is a kind of radar antenna. So radar antenna, as I have told you, it is a circularly polarized antenna. So generally a helical shape, if I use a helical shaped wire and if I feed that helical shaped wire with a particular AC frequency, then it will give out a circular polarized wave. So that is why you see in this picture a helical shaped wire is wound on a substrate, on a radome. Okay, this upper part is the ground plane, and the radome is fed from the bottom part to this coaxial cable, and one part of the coaxial cable will be grounded over here. So these kinds of readers are circularly polarized readers. Oh, this is another kind of, now see, this reader is a three-dimensional reader, which is having quite a amount of volume, which is having a considerable volume. But for example, if the volume is a kind of constant for some design, then we can go for some planar designs like this. Here, see, there is a substrate taken, and on that substrate, there is a conductive ink that is pasted on the substrate for giving some circularly polarized radar antenna design. Okay, so these are planar kind of radar antenna designs. So radar antennas are both non-planar like this and planar like this. So different kinds of radar designs you can do. So the first part ends over here. I'll continue in the second part and I will talk about vehicle management system as a whole with RFID system the next day. Okay. So till now, do you have any questions? If yes, then you can ask me. If you have any questions, then you can ask me, or you can ask me after I finish the lecture. Okay, then. Thank you, everyone. We'll meet again tomorrow.
Thank you, Dr. Ghosh, for delivering your lecture.
Thank you.
So again, tomorrow you have got another session of him, so you can ask the questions tomorrow itself. Now we will break for lunch, as indicated. We will again catch up at 3 p.m. by the lecture of Dr. Kaushal Kumar Jha. So we will break away for lunch right now, and we will again meet over here at 3 p.m. with lecture of Dr. Kaushal Kumar Jha. So I will see you again at 3 p.m. Bye.